We had a look at the idea for areas. Now we're going to use integration to work out volumes of unusual shapes as well. So again, I've got a random function here, and I'm going to rotate it around the x-axis to get, well, some sort of weird shape. Let's rotate it. Woo! Hey, was that impressive? Yeah. What is it? I don't know, one of those things you put flowers in. That's them, a vase. Well, I was going to say vase, but I thought you'd laugh at me. That's it, I was right. So the question is, how do we find this volume? Now, remember with area what we did is we treated it like a series of rectangles and summed them up. So here, if I was to chop this shape up, I wouldn't get rectangles, I get a whole heap of circles. In fact, there'll be circles with width, in other words, a cylinder. So here's our formula. Volume of a solid of revolution about the x-axis is pi y squared dx. Going around the x-axis, it's dx. Y squared.
Pi r squared.
Exactly. Formula for a circle. Pi r squared, and the radius in this case would be the y value. Okay. Pi, of course, is a constant, and we saw we could take constants outside the integral sign. So that's just why the pi's in front. And if we're going around the y-axis, then the radius would now become the x value. So we get pi x squared dy. Now in extension 2, we'll see this in a lot more detail. And we can also find a lot more interesting shapes other than just ones that have circles. But in 2 unit, and 3 unit for that matter, we're pretty much restricted just things being rotated around the x-axis or being rotated around the y-axis. And in 2 unit or 3 unit, it is okay to quote those formula. We're going to prove the formula for a cone. Before now, you've just taken it to be true because you're good students and you believed your teacher. And your teacher said it was a third pi r squared h, and you went, well, if the teacher says so, that's what it is. We're going to prove it. Because if I was just to get a straight line going through the origin and rotate that, I'll get a cone. So I'll conveniently call the x value h, because that'll work out to be the height of the cone. So I've said our formula is pi times the integral of y squared dx, because we're going around dx. It never gets old, does it? Okay, now, let's sub in. Y equals mx becomes m squared x squared, and we're going from 0 to h. Well, m squared, of course, is a constant as well. That's just the slope of the line. So I can factorise that out, add 1 to the power over the power, third x cubed, substitute in h, substitute in 0, and there's our formula for the volume of a cone. And you're probably looking at it going, that's not what I remember it to be. A third pi m squared h cubed. Well, that's because we don't normally talk about the slope of the cone when we do the volume. So how can I fix that up? Well, remember, the slope here, I could say, is rise over run. The rise would be the radius over the run would be the height. So I could substitute in for m, r over h. And when I do, now it becomes our familiar formula. There it is, a third pi r squared h. Isn't it great? Let's work out the sphere one. Who remembers the formula for a sphere? Right. Now, if I rotate this, I could go around the x, I could go around the y, it doesn't really matter. I'm going to get a sphere. There we go. So y squared, well, if I rearrange the equation of our circle, y squared becomes r squared minus x squared. Because of symmetry, I'm just going to go twice from 0 to r. And obviously integrate. R squared's a constant, so I get r squared x minus a third x cubed. Substitute in r, substitute in 0. There it is. 4/3 pi r cubed. Pi r cubed. Right. Let's have some unusual shape that we don't actually know, a parabola. When we rotate that, the volume of the solid generated y equals x squared is revolved around the y-axis, and we're going to go from 0 to 1. So there's our parabola. We're going to rotate from 0 to 1, and we get the shape known as a paraboloid. Pi times the integral of x squared dy, because we're going around the y-axis. Why the y? Add 1 to the power over the power, so y squared on 2. We're going from 0 to 1, and there we go. Units cubed, of course, because we're talking about a volume. So pi on 2 units cubed. Now, let's have a look at this shape. It's the shaded bit, the bit I've got shaded in blue. We're going to go about the x-axis. So when I rotate that one, I've got to be careful because it's actually the area above the line that's going to create the solid. So what I've really got is area between two curves that I'm rotating. The top boundary is simply the line y equals 5. The bottom boundary is the line y equals 5x. So just like we did for area, when it's between two curves, top one minus the bottom one. But what we've got to be careful with is we square it before we do the subtraction. Because we're saying the volume of the line minus the volume of y equals 5x. So it's 5 squared minus 5x all squared. So 25 minus 25x squared. And now it's just like any other question. Add 1 to the power over the power. Sub in 1. And we get 50 pi on 3 unit cubed. I lost my S. Oh. There is a quicker way, of course, for this question. Because if you rotate a horizontal line, what are you going to get? And we have a formula for that. If we rotate that diagonal line, what do we get? And we have a formula for that. So I could have said it's pi r squared h minus a third pi r squared h, which is 2/3 pi r squared h, and there's my answer. So if you recognise the shape, use that to your advantage. Save yourself some time. HSC one. We got two parabolas, one upside down, one the right way up. And first part of the question, find the points of intersection. So we would solve them simultaneously. So x squared is 12 minus 2x squared, plus or minus 2 we get for our answers. But that's not the point, of course, that's just the x value. So it turns out to be 2, 4. And I guess I probably got the question wrong because it also makes it minus 2, 4, and I didn't write that down. But it does say find the points. All right, next part. That shaded bit is going to be rotated around the y-axis by splitting the shaded region into 2. Why do we do that? Because the boundaries change. If we're going around the y-axis, imagine you're going up the axis. So it's the concave up parabola going to the axis. Concave up, concave up, concave up. We get to the point of intersection, but now it's the concave down parabola. So it changes the boundary. If it changes the boundary, we've got to split it up and find separate volumes. So, all right. Well, they do say or otherwise, so perhaps there's another way of doing it. But anyway, let's do it. Pi times the integral of x squared to y, going around, you get the idea. There's the red line where I'm going to split. So this one here, x squared is y. I'm making x squared the subject because that's what I'm going to substitute in there. I haven't bothered making x the subject. So it's just simply x squared equals y. My other one becomes x squared is 6 minus a half y. So it will be the addition of the 6 minus a half y and the y. Add them together. Well, integrate them first, of course. Substitute in. Add them together. And we get 84 pi units cubed. All right. So 11g. Really, once you come up with the integral, it's much the same as we've been doing in all the other exercises. There's no new skill there. I guess the skill is working out what you're rotating, where the boundaries are, do you need to split it up, those sorts of things.